Chapter 6, Section 1, Area of a Region Between Two Curves. Now this would be our last chapter, although I say that term loosely because this last chapter we're really only taking two sections out of Chapter 6, a section out of Chapter 7, and then a couple additional sections, one on net change, one on slope fields, which can be found throughout different places in the textbook. But all the same, we are at the last chapter. Okay, we started talking about the area under a curve back in Chapter 4, and what we're going to do is we're going to kind of alter it just a little bit, because before, when we found the area under a curve, we found it under the curve but above the x-axis. Now what we're going to do is we're going to look at it between two curves, and the idea being behind this is that to find the area here that's shaded in, I find the area under this curve, the whole thing, which is this guy right here, the integral from a to b of f of x dx, and then I find the area of this unshaded region here that's underneath the red curve, y equals g of x. That would be the integral from a to b of g of x dx. And then I rewrite this as a single integral by taking the integral from a to b of f of x minus g of x quantity dx. Now, we know that when you have the integral of a difference, that it's the difference of the integrals. Well, I'm just reversing this. Here's the difference of two integrals, and it's the integral of the difference. So what we'll do to find this is very much what we did before to find the area under a curve. We partition the subinterval from a to b. This is from a to b. Now we can make this a regular partition. We can make it an irregular partition and have each of the subintervals of different sizes. So because of that, you'll notice here that instead of saying delta x equals b minus a over n, where n is the number of subintervals, I have delta x as delta x sub I, which is the difference from the right endpoint minus the left endpoint. So that way you can have a partition that's not all the same size. So what we're going to do, we're going to let the number of subintervals increase, but because of that, we don't have to use a left endpoint, we don't have to use a right endpoint, we just need an x value somewhere in that subinterval. So we pick c sub I, that would be any value in here, it could be at one of the endpoints, such that c sub I is between x sub I minus 1 and x sub I, because this is just, I call this the ith subinterval here. And we're going to find the area of the rectangle. Notice the rectangle that I've drawn in here, this is my representative rectangle, as base times height, or length times width, or however you want to think of that, by taking this y value and subtracting this y value here, so that I get this height right here. That's this guy right here. So at c sub I take f of c sub I minus g of c sub I, being that f of x is, the top one and g of x the bottom one here. I just put it in the first quadrant for convenience sake, by the way. And then that's times delta x sub I, which is this width. So it's base times height, or length times width, however you'd like to think of that. And that guy right here is the area of this rectangle. So if I do this for each one of my subintervals, what I'm going to have then is I'm going to have the sum, as I goes from 1 to n, of the difference here of the y values, the f of c sub I minus g of c sub I, times the width of that subinterval. Now, as I mentioned, we're going to let n get big and big and big without bound. So we're going to let n go to infinity. So that means that the limit, let me see if I can move this here just a little bit, that the limit as n goes to infinity of the sum of all these areas of rectangles here turns out to equal, because that's how we typically come up with an integral, we approximate, we take the limit, and we integrate here from a to b of f of x minus g of x dx. There's your height, there's your base right there. So we'll need a formal statement of this, so I'm going to go ahead and move this off to the side. And here's my formal statement. The area of a region between two curves, if f and g are continuous functions on the closed interval a, b, and we'll say for convenience sake here that we'll say g of x is less than or equal to f of x for all x in that subinterval from a to b, or in that interval from a to b, then the area of the region bounded by the graphs of f and g and the vertical lines x equals a and x equals b is given by, and this is what I had just a moment ago on the other page. Okay, now it doesn't matter, as it turns out here, if both functions are above the x-axis, or if both functions are below the x-axis, or if one's above and the other one's below, just as long as you have f of x is greater than or equal to g of x for all x in the interval from a to b inclusive. Now the representative rectangles that are going to be used in this particular chapter for the different applications, and this will go for the applications in section 2, section 3, which we don't have to cover, section 4, which we don't have to cover, section 5, which we don't have to cover, is that a vertical representative rectangle will be integrating with respect to x. That's my diagram here from my first example. I have a vertical, height-wise vertical representative rectangle, but we could have a horizontal representative rectangle, and in that case then we're doing everything with respect to y. So I'll try to show you at least one example of each. All right. Now I have found it convenient to make a sketch, because if I have a sketch of what's going on, then typically I can picture what's going on. I know which graph's above, which graph's below, and all that kind of good stuff here. So I would probably suggest that you make a sketch. It doesn't have to be perfect, but that you make a rough sketch to get an idea of what's going on here. So I'm going to find the area of the region bounded by the graphs y equals 2 plus x squared. That, of course, is a parabola that opens upward. Y equals the opposite of x. That's a line that goes through the origin and has -1 slope. X equals 0. That's the y-axis, and x equals 1. There's another vertical line. So just kind of rough. I'm going to try to make a sketch here best I can. And let's see if I've given myself enough space here. Probably not. I may have to make the y values worth 2. This is going to be worth 1 here. So let's see if we need to make it 2 here. So if I wanted to graph y equals 2 plus x squared at when x is 0, because we're going from x equals 0 to x equals 1. When x is 0, I'm at 2. When x is at 1, I'm at 3. Actually, I guess I could have probably squeezed her in, so we'll just put it right here. And because it's a parabola, I know it's a curve. And then we have this, this, and this. Oh, no, we don't have the bottom there. Take that back. We have the vertical line, x equals negative, y equals the opposite of x, so that would be a line that kind of goes like this. So it goes to here, but it's going to come all the way down to here. Almost messed that one up. And this point being right here, when x is 1, y is opposite of 1, so it's not drawn very well, but this point here being 1, -1. It's supposed to be 1, -1. So this is the region that I am going to try to find the area of. So I'm going to integrate this from, I'm doing this with respect to x. My representative rectangles would be vertical here. This y value minus this y value for the height. And so I'm going to go from 0 to 1, because those are what my x values are changing from x equals 0 to x equals 1. Of the height here, which is the difference in the y values, which is the difference top minus bottom of the y value. So I'm going to write 2 plus x squared minus the opposite of x. And then, of course, that's times my thickness. That's delta x here, so dx. Now, that's not so bad. I'm going to rewrite it real quickly. I'm going to go ahead and write this from 0 to 1 of the quantity x squared plus x plus 2 dx. I'm going to integrate. I got a nice little polynomial here. You will typically have some fractions, so be careful with your arithmetic. So I get 1/3 x cubed plus 1/2 x squared plus 2x when I integrate. And I'm running from 0 to 1. If I plug in 1, I have 1/3 plus 1/2 plus 2. Minus, if I plug in 0, I just get 0. So let's see, that's going to be 5/6. 2 and 5/6 would be 17/6. And because it's the area, I'm going to write square units. I don't think you need to do that, though. Write the square unit symbol on the AP test. I like to do it, though. All right, and there's my first guy. That would be this area right in here. All right, now let's try to find one here. Now, all we are given are intersecting curves. Before, I had some vertical lines that kind of limit what my curve was, but here it's going to be these two lines that are going to, or these two curves that are going to be intersecting. This, of course, is a curve. This is a line. So here's another parabola. This one opens downward, and y equals x. I know what that looks like. Y equals x as a goes to the origin, slope 1. So I'll make a sketch here, see if I can do a better job on this one than I did on the last one. I'll make it a little bit bigger. Maybe that's the key. Let's try this. Let's see what happens if I go here. All right, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. Let's see what happens here. Make them 1 and 1. So let's see. Y equals x looks like this. This is just a rough sketch. And this would be a parabola with vertex at 0, 2 that opens downward. Let's see. If I plug in 1, I'm at 1. That's this point right here. And then here, if I plug in 0, let's see, if I plug in -2 here, I'm at -2. Oh, look at this. That was sweet. My curve is going to go something like this. But you can see the area between the two intersecting curves is this area right here. So I have a top curve and I have a bottom curve, and that means I'm going to have a representative rectangle that's going to be vertical, delta x here. I'm going to do my integration with respect to x. But what are my x values changing from? Well, they're changing from the x values of these 2 points, because that's the smallest x value, that's the largest x value. Now, it looks like this is 1, 1, and it is. And it looks like this point here is -2, -2, and it is. But if it's not so obvious, set this equal to this, solve the system simultaneously, and find those x values so that you can determine what your x's run from. So in this case, my x's are running from, let me erase this up just a little bit, from -2 to +1, from -2 to +1. Top minus bottom would be the quantity 2 minus x squared minus the bottom y value, which is just x. This doesn't look a lot different than the integrand from before, signs only. Let's see, let me rewrite this. This goes from -2 to 1. I'm going to write this as the opposite of x squared minus x plus 2. I just like descending order when it's convenient. So up to 3 over 3 gives me -1/3 x cubed minus 1/2 x squared plus 2x. And I'm running from -2 to +1. Definitely going to get some fractions here. This is going to be, let me raise this up just a little bit. Plug 1 in. I'm going to get -1/3 minus 1/2 plus 2 minus, and then I plug -2 in, and I'm going to get +8/3 minus 2 minus 4. So that's -5/6. That's 12/6. So this is 7/6 minus, now that's a -6 here, which would be -6 here would be -18/3. So I have 8 minus 18, that would be -10/3. So this is 7/6 plus +10/3, or let's write 26. So I get a common denominator. So I have 27/6, which is, divide top and bottom by 3, 9/2. So the area would be 9/2 square units. Let's see if you can see that. Let me check the screen. Yeah, you should be able to see that okay. I really believe you'll be helping yourself if you make a sketch. Now, sometimes it's inconvenient to sit there and plot points, but you could always use a graphing calculator to double check. All right. All right, now, this one's got a little bit to it, because in this particular problem, the curves here, notice it's a cubic, and notice it's a quadratic here. So I know what this looks like. It's a parabola that opens downward. But over here, this is going to be one of those S shapes. It's going to probably look something like this. So to come up with a reasonable sketch here, you might have to plot a few points. But what I would suggest is find where they intersect first. So I'm going to set the y values equal to one another. I'm going to set 3x to the third minus x squared minus 10x equal to the opposite of x squared plus 2x. I'm going to bring everything to one side. I get 3x to the third. Looks like the x squareds cancel, and it looks like it's going to be minus 12x. Well, this is going to factor nicely. I have a GCF of 3x. Oh, really nicely. Difference of squares. And it looks like I'm going to have 3 points of intersection. Now, what does that mean? 3 points of intersection, I should only have 2 that kind of, enclose it. Well, what that might mean is that you might have a situation where the one graph is not always above the other. It's only above the other for part of the time. So here again is why it's so important to come up with a sketch, a reasonable sketch of what's going on. Now, as it turns out, I had plugged this into and Googled this, and I got this sketch. I found a problem done online that had the same exact two, it wasn't the other way around, I didn't model it after this, that had the same two graphs, and you can see the parabola that opens downward, and you can see the kind of sideways S shape here, and you can see the two regions. So it's really important that you come up with a sketch, because I'm going to have to do this problem using two integrals, because it has to be top minus bottom here, because I have vertical, I'm setting this up with vertical representative rectangles, whether the representative rectangle is here or whether the representative rectangle is here. It's got to be top minus bottom. Now this guy here, let me use a green pen to highlight this. This S-shaped curve here, whoops, that's this guy right here, and of course this parabola right here, that's this curve right here, that's this function right there. So I'm going to have to break this into two integrals. I'm going to have to break this into this integral here for this part and this integral here for this part. So what's above and what's below is going to change here. Here it's the cubic above the quadratic, here it's the quadratic above the cubic. So notice here at 0, -2, and 2 are where my points of intersection are right there. There's -2 something. At 0 that looks like 0, 0. And at 2 that looks like 2, 0. So to figure out what this value is, I would have to plug -2 into one of these. That would be what? -4, -8 it looks like. I don't really need that y value, but if I'm making a sketch it helps. So now I'm going to use this graph to set up my integral. So I'm going to kind of scoot it over to the side here just a bit. And I'm going to do my first integral. Can we see this okay? We can. From -2 to 0. The top being the cubic, so that would be the quantity 3x to the third minus x squared minus 10x minus the bottom, which is the quadratic, and that would be the opposite of x squared plus 2x. See if I left myself enough room to get the second one in. I did not, so I'll have to put it down below. Then, let's go back to the sketch here. I have to do this region, so I'm going from x equals 0 to x equals 2. And it's just the other way around. It's just the opposite. So that turns out to be the opposite of x squared plus 2x minus the quantity 3x to the third minus x squared minus 10x. And I'm going to have to evaluate this integral. I'm going to have to evaluate this integral. And then I'm going to add those two amounts together. And they better both be positive because of the way I set this up, top minus bottom. So the first one here, from -2 to 0, let's see, if I simplify this, I get 3x to the third. The x squareds are going to cancel. Looks like minus 12x dx. And then for the second one, it's just going to be the opposite, 0 to 2, because it's this top minus this bottom, which is just reversing the subtraction. And that's going to give me 12x minus 3x to the third. Might get some fractions here. So up to 4 over 4 gives me 3/4 x to the fourth minus up to 2 over 2 minus 6x squared, running from -2 to 0. And then over here, this is going to be 6x squared minus 3/4 x to the fourth, running from 0 to 2. I like those zeros though, because when you plug 0 into here, this is just all going to be 0 minus, and then I plug -2 in. -2 to the fourth power is 16 times 3/4 is 12. Minus -2 plugged into there, that's going to be a positive 4 minus 6 times positive 4 minus 24. Plus over here, I plug 2 in, that's going to be 24 minus 12. Minus, if I plug 0 in, I just get 0. Nice. All right, so what's going on here? This is going to give me -12. The opposite of -12 is 12 plus 12 again. Kind of neat. They look very different, but they have the same area. They're both area 12 square units. So that gives me 24 square units. And there's my answer there. All right. Everybody good? All right. You can always go back and watch the video a second time if you need to here. All right, now let's try one here that has, oh gosh, kind of getting ahead of myself here. I don't think I have done an example yet. I have to make sure I do an example. No, we're good. I think I've just haven't done one where it's done with respect to y, where we have horizontal representative rectangles instead. So let's do this one here. And I have x equals 3 minus y squared and y equals x squared minus 1. Of course, that's a line. Slope 1 goes to 0, negative 1. That's a parabola, but it's not a quadratic function. It's a parabola that opens, I believe, here to the left because of the negative in front of the y squared. I think I got a diagram of that. In fact, I found this problem actually worked out online. It's kind of faded, so it's hard to read all this stuff, but you can at least see my diagram because I emphasize that. Here's the parabola. This is the x equals 3 minus y squared. It's convenient when you can find these online, but you need to be able to do these whether you can find them online or not. You should be able to grind them out. So I have a sketch here, but notice it's not top minus bottom because in this case, top minus bottom, this is top minus bottom, top minus bottom, top minus bottom, but here, top minus bottom is the same function. Now, not that it can't be done, but it's just more difficult to break this into two integrals where you have the top half minus the bottom half for this part from 2 to 3 here. So my suggestion is make a representative rectangle that is horizontal. So this is delta y. So everything's going to be done in terms of y. So now what I'm going to do here, I need to know these points of intersection. Okay, so I'm going to set the x is equal to one another. This x, by the way, is equal to y plus 1. So I have 3 minus y squared equals y plus 1. I have y squared plus y minus 2. I have y plus 2y minus 1. So I get y equals negative 2 or 1. So there's my y equals negative 2, although, oh, excuse me, my y equals negative 2 right here. So this point is something negative 2. I'm not sure what it is. For the x value, don't need it. And then right here, my y value here is 1. And this is something, comma, 1. Although that wouldn't be as difficult to find. Let's see, if I plug a 1 in here for y, I get x is 2. If I plug a negative 2 in here for y, I get a negative 1, looks like. All right, so now I'm ready to set up my integral. Let's see, bring this over just a little bit. So I have the integral here. Can you still see your diagram? I'm trying to do this so you can get the best of both worlds here. There we go. I'm going to set up my integral. This is going to go from negative 2 to positive 1 with respect to y. All right. And it's going to be not top minus bottom, but right minus left. That's how I'm going to get a positive direction here. The bigger x value minus the smaller x value. So in this case, the bigger x value is from the parabola. So that x value, in terms of y, is 3 minus y squared. And then I subtract the x value that's to the left there, which in terms of y is y plus 1. So in parentheses, y plus 1. Right. Check that out. That's a little different. It's not top minus bottom. It's right minus left to get the height there. That's the height. That's the thickness or the width, the base. All right. So now I'm going to simplify this before I start to integrate. This goes from negative 2 to 1. What would that be? The opposite of y squared minus y plus 2 dy. So negative 1/3 y cubed minus 1/2 y squared plus 2y running from negative 2 to positive 1. Let me move this up just a little bit here. So I'll plug the 1 in and I get negative 1/3, sorry it's so sloppy, minus 1/2 plus 2 minus, then I'll plug the negative 2 in. So that's going to give me 8/3 minus 2 minus 4. This looks familiar, like I had the arithmetic on this same exact kind of a deal here once before. Oh, I did. Look at that. It's the same numbers. It's the same numbers that I had right there. So this turned out to be 9/2, and this would be square units for the area. There's no substitute here for not practicing these problems. This is definitely on the AP test. It's most likely going to be one of the first problems on the free response. They'll typically give you a region with bounded by a couple of curves. They'll want you to find the area of the region. Then they'll maybe revolve it around a vertical horizontal line, and they'll be asking for volume of a solid revolution, which is actually in the next section that we're going to cover. So this is something that appears almost every single time. I can't remember the last time I saw one where a pre-response AP test where it didn't have it. So practice, practice, practice.